Luca. Luca Forte is joining, but okay. So welcome everybody. Matteo Bordin here, speaking about optomechanics and the things I do with optomechanics. I thought to start with was be interesting to give a bit of an overview for optomechanical systems. I pretty much assume that we are all familiar with what they are. So optomechanical systems are some very recently developed systems, and the example we all know is LIGO. LIGO is fundamentally an interferometer that is also not optomechanical, a very big one. There has been a lot of study on the effects in LIGO, and after that there has been some effort in the research to miniaturize the system to exploit the effects that people have seen in the first place with LIGO. So optomechanical systems from the birth originally as a great sensing systems. They're very good for sensing, also for very small pulse sensing, and they are developed as anti-level system, optomechanical cavities, there are particles. There's a plethora of here is a scheme for all optomechanical systems you can find. And they're also very useful for quantum communication because they are great optical transducers, so they can transfuse from teleport frequency, from light reaching the cavity, to lower frequency. They are easier for working with them. And they also can work as optical memories where the mechanical component can store a photon, can store the state of a photon and release the data. So they have many applications. There's a lot of interest on that. Basic principle and successes of the system is that the basics in interaction is radiation pressure. So at a classical level, it's electromagnetic radiation transfer energy to a mechanical component, which is free to oscillate. For example, here is a mirror is free to oscillate, and here is light transfer energy. At a quantum level, it's scattering between photons and vibrational modes of the mirror. If it's more than enough, the vibrational modes are quantized, so it's quantum interaction. Some successes that have been achieved with this is a mechanical component equal to the ground state. So quantum ground state, very few photons in the ground state, less than one, and many applications will be less than 10 to minus 1 photons, and also quantum effects observed in macroscopic masses. Now this is interesting because even to the nanoscale, this system can be considered macroscopic compared to quantum particles. So to particle electrons and photons or molecules, they have masses that LIGO masses are of the order of kilograms. These masses are of the order of picograms or nanograms even. So seeing quantum effects and things with masses of nanograms is pretty impressive. Now, what I'm going to talk about mostly is macroscopic superpositions. First of all, why macroscopic superpositions are important? First of all, is for fundamental tasks, just a measurement problem, like creating stuff. I found this image, this surely I generated the laser that I love it. So it's called Schrödinger cat stuff. A lot of attention on gravitation-induced entanglement. For gravitation-induced entanglement, one wants to see if gravity is able to generate entanglement as a proof of the quantumness of gravity. And to observe these entanglements, one needs two massive components, because one can observe better gravitational effects with bigger masses, so big masses, prepare a superposition, as in this case, a spatial superposition. So again, interest for macroscopic superposition. Also, there is a continuous quantum localization theories that are phenomenological theories, so they have some parameters, and this is a parameter space. They need to rule down the different spheres. By creating macroscopic superposition, one can rule out some other parts of this white arrow is left to shrink the parameter space. Now, what is quantum? What is macroscopic? A bit of definitions here. First, we will talk about different functions. We talk about different functions because this is a quick and easy way to benchmark the state is quantum. Dignal functions that exhibit negative regions can be, we can say that they do not have a classical analog and they are in a quantum state. For example, here I plotted the dignal function, the profile of the dignal function of a vacuum state, and here is the dignal profile of the dignal function of the single focus state. Here that is a pretty small one, the x-axis. So you can see single focus state, pre-quantum, negative region, and there is also a size of the superposition. And the size of the superposition, here is much more general, but I think it's introduced also with clearly. The size of the superposition scales as pretty much as the size of the part of the boundary that is proportional to the mass. So here we have to make a trade-off between what macroscopic things we want to see. Macroscopic, spatially well-localized macroscopic superposition, we can all be achieved with very small masses. If we go to big masses, the macroscopicity of the superposition will be basically the size of the photon, so of the radius of the photon, so very small. Achieving well-localized quantum superposition of very big objects is the challenge. So this is the difficult thing to do, because there is this trade-off between masses. Either very small thing, very localized, or very big thing, very small, very localized. And this is also an active research. There are plenty of people that, especially with levitated particles, they try to flash them with lasers, they try to play with Super Mario in Vienna. There's a lot of things happening on this field. Is very active. So I also joined the efforts in this field of research, and this is the setup we will work with. Now, this is an ugly capacity, so this is the field of capacity, this is a spring, so this is physical state. First, we cool down the.
What's the state nearby your computer? Otherwise, the people online can hear.
Oh, sorry. Yeah.
Okay. Sorry.
First, we use a laser to cool down the mechanical oscillator, close to its ground state. So it's going to be a thermal state, very small Fisher number. And then we use a different laser, different frequency. We'll get back to this just to give you an intuition of what's going to happen. We use a different laser that has a probability to generate entanglement, correlation, strong quantum correlation between the mechanical component and the field inside the cavity. Okay? And then after these two has been correlated, we detect the blue laser on a Geiger detector that does photocounting. We'll get back to why this is useful, but this is just a scheme I'm going to talk about. So, to talk about this, we need to introduce some tools, especially Hamiltonians and Hamiltonians pretty much, and dynamics. So here on the top left, there's the Hamiltonian of a closed system optomechanical system, of a closed optomechanical system. So in all this patient, everything works perfectly. We're in an ideal world, and everything is beautiful patient because there's a cubic coupling where they couple the photon number is a cavity, A, with the position of the mechanical oscillator. Now, one can show that if I do the unitary evolution of a vacuum state of both and the Hamiltonian, I get very quantum state, very negative Wigner function upon optical measurements, and these are some examples. So if I let things evolve under this coupling, and then I do optical measurements, a measurement of the light that goes out from the cavity, this is perfect, this is beautiful, it's very, like, we get very negative Wigner function. Problem is, this G0 is usually much smaller than the optical dissipation. There is a real world effect, so the time scale on which I see quantum effects is ridiculously small compared to the time scale on which the coherence kills everything. So this Wigner function here, nobody is nowadays able to see it. We can see it's a technical problem, but there are also other methods. Before proceeding, this is a real world setup, very A is the cavity mode, B is the mechanical mode. They interact with G0. They oscillate with capital omega, and delta is the cavity tuning. Tuning between the cavity frequency, between the cavity frequency and a drive that drives the cavity. Sorry.
Can I ask you why you do that? Like, why is the cavity always smaller than the gate? Like, even the start, like, when you touch the house,
well, G0 is a general statement for the optomechanical stuff we're interested in. Because G0 is depends on the 0-point fluctuation size of the mechanical state. This, as I told you, depends on the mass, on the inverse of the mass. So very big masses, naturally this G0 will be very, very small, very, very small. We can do optomechanical system, there's a limit to what you can miniaturize. So very, very small masses, there's still a limit of computation that you can achieve.
You cannot reduce the decay rate.
Yes, this is a very point. That's a very point. There's always a trade-off here. Like optical cavities are things that someone needs to fabricate, and usually the parameter that's going to decay rate is the finesse of the cavity. Currently, with the best possible cavity, the highest finesse possible, this is still happening. And also, if I take an ideal cavity with nothing goes out, this is beautiful, but I will never be able to measure anything. So there's a bit of a balance to be done. If I have no output for the cavity, because I won't be able to see. So yeah, no, this is surely a good point. I would love to be able to say, oh, of finesse, 10 to the 7, yes, beautiful, but nobody makes it up. So yeah.
Sorry, and the dissipation of the mechanical mode does play any role? Does play any role?
Dissipation of the mechanical
mode?
Yeah, does play a role. Usually, like nowadays, there are such high quality factor data that to give you an order of magnitude, K kappa is of the order of megahertz, gamma is of the order of 10 hertz, 100 hertz. And this is common practice to be achieved in non-scale of mechanical systems. They have the mechanical component have extremely high quality factor. So these gamma, if the thermal bath, the temperature of the bath surrounding the mechanical system is not too high, can be considered like not the main source of the coherence. We'll have to take account of this, but it's not the main source. It's usually kappa as well.
And is it always fair to say that the two dissipation rates are independent, or?
That's a great question.
I mean,
well, they dissipate in different environments, and this is a really, really good question. I don't know how to Yes. Well, moving the length of the cavity is the principle behind the optomechanical coupling. It does not have any dissipative effect. Also because usually, realistically, this mirror here is much, much smaller than this one. This one is semi-transparent, so the light will get in and get out. Well, this one is coated so well that this one will not have, basically no leakage. So all the leakage of the dissipation will happen through this one. And the cavity lens will decide what introduce any position-dependent dissipation. There are people that have worked with position-dependent dissipation. I am not really aware of what does this physically correspond to. Something I just don't know. Okay, so here introducing the parameters we'll talk about: optical dissipation, mechanical dissipation, oscillation frequencies, and the driver. So why the driver is important? Because it does the job, it does the trick. If we introduce a coherent driving, a very bright one, very strong one, the cavity gets full of photons and it gets a semi-classical rotation number of cavity. There's a lot of photons inside, impinging on the mirror. So we're just by the center of approximation, and alpha, that was that. Alpha is the mean field, the semi-classical setup. That does something very interesting, that is amplifying the coupling. So G, the last line, because G becomes alpha G0, G naught. So alpha can increase the coupling strength orders of magnitude. So that's why usually that is common practice to have this coherent drive. There's also a price to pay. The price we pay is that we lose the non-linearity of the interaction. We linearize the interaction, so the interaction can be G naught A by Q, now you get G phase quadrature of the field, position of the mechanical state, which is now quadratic, it's not cubic anymore. So we find the linearities. This is when we write the equation of motion, and this is exponent, that will be linear. So no Wigner function to free anymore. Obviously, we'll come to this back later. So a couple of comments on the consequences of this. I think it's very clear if we write the instruction of Hamiltonian in the instruction picture. And through this we can clearly distinguish two resonant processes. These two resonant processes happens at the first one at the tuning equal to the Hankel frequency. That is this red one, red is a right one, red. I'll come back to white, red, and blue. And this one on the tuning equal to minus the Hankel frequency is the left one. These two processes correspond to two different couplings. One is beam splitter coupling, the other one is two-mode squeezing coupling. So we have two very different dynamics depending on which frequency we tune. And I think it's interesting, in this case, this is the, I plotted here very roughly, but this is the output spectrum we have here. So here, the central peak is just the light that goes in, interrupt by radiation pressure, so it just pushes the mirror and goes out. The sidebands, these two pieces over here, the sidebands, are explicitly quantum processes. So it's quantum scattering. The light goes in, it scatters, and goes out at a different frequency from which you get it. This is the same frequency minus omega, minus omega. This is the outgoing incoming frequency plus omega. We'll come back to the second, but this ratio between kappa and omega is really important because if kappa is greater than omega, we wouldn't be able to see the sidebands. We wouldn't be able to see the peaks. So our working condition is very important is that we need to have omega greater than kappa, so that we're able to resolve the sidebands. We're able to see them on the output. Last comment, we will like to select one of the two interactions. To select one of the interaction, we do the rotating wave approximation. The regime in which we can do this and we can neglect the non-resonant one requires that we are not driving with too much power instead of that. We'll back to this, but there are conditions under which we can neglect one or the other. There are also conditions in which we cannot neglect them. Just a comment, Langevin equation, voila. I guess we're quite familiar with this. These are the equations of motion, written in terms of the quantum noises, plasma noises. These are the equation of motion with the Hamiltonian before. We introduced the cavity dissipation and the mechanical dissipation, kappa and gamma. And we have introduced the stochastic terms. This psi of t is a thermal node, no Markovian. Guess Markovian quite different Markovian. And this 8 is the quantum input noise, where the only non-zero correlator is this one. And it's the delta correlator noise, white noise, from the vacuum fluctuation getting inside of it. We will use this in a second, but we will approximate them, but this just important to mention. Okay. Now, after this introduction, we are ready to talk a bit more specifically about the protocol we're working with. So, first of all, we need to define the pools. First, I just want to mention a thing more about this. So, the first pulse we use is a pulse resonance with this segment here. Why? Because we select two beam splitter. The beam splitter has the effect of dragging excitation away from the mechanical space, and the cavity quickly dissipates that. So basically, the cavity is absorbing excitation from the mechanical space. This is the principle of sideband cooling. So the first laser is red, the tuned is a resonant with this one. That's why it was red, that's all that helps. And it cools down the mechanical space. The second one is blue tuned, so it's resonant with the other sideband, and generates entanglements. Okay? So that's why colors matter. They are a different frequency. I'm driving the cavity in different frequencies. Okay, so basically, just say I think say it quite straightforward. Here I'm saying I'm considering I've already shined the first pulse, cooled down, and I'm shining the second one. Second one is a squared pulse, similar to a square pulse, detuned at minus omega on the blue one. Now, this is the justification of the regime I'm working with. It can be summarized in this. Now, omega greater than kappa. We saw this already. This is the resolved side of the regime. We want to see it. Omega greater than G is a regime where we can apply the rotating wave approximation. So here we can select 1, 2, and then the other. Kappa greater than G allows for not having stability problem. I won't get much into this. It's interesting. But simply the cavity loses photon much faster than it can accumulate. So you don't have stability. And the last but least, it's the thermal coherence, right? And basically we're saying everything is faster than this one. And if the pulse is also shorter than this one, we will simply neglect thermal coherence for now. We'll say this is so small, we're keeping such high quality factors, it's so small, and the battery is so cold, the thermal battery is so cold, that for the time scale we're interested in, there's no thermal coherence. Also, we can linearize the thing I was saying before, and formalize much further. I just want to say we can linearize the corruption, and the amplified coupling depends on the photon inside the pulse, related to the density of the pulse, and the duration of the pulse. And so I'm now justifying in the pulsar scenario whatever I just said 5 minutes ago about the linearizing dynamics. So back to our friends, Langevin equation. These are the beautiful Langevin equation, neglecting the coherence, and written the interaction picture. So there's no oscillation term anymore, it's just downward interaction. Here, one will do a trick that is adiabatic limitation. Why we do this? We say that K is greater than G, kappa is greater than G, so the cavity basically decays so fast that it is always in a steady state. Even if for excitation of the, or even for the evolution of the mechanical component, the cavity just follows the mechanical component. Easy approximation, but nice approximation allows us to solve the dynamics. So this is the key point. We are now able to, under this approximation, this regime, to solve the dynamics. And we are able to solve the equations of motion for the photon and phonon modes. With an effective calculator that is now G squared over 2K. They will come back to this later. Now, very quickly, this is input-output relations. Since the cavity basically is enslaved to the mechanical state, to say that the mechanical happenings, the intuition is just following the mechanical motion. What we want to achieve now is eliminating the cavity and looking only to the correlation between input and output and the mechanical. And we do this through input-output theory. We can define temporal modes for the input and the output. There's a bit of math here. Like it comes very, I don't know, I think I can explain here. It comes very natural from this term here. And from the cheesy. It's just mathematical detail, it's not really interesting. The interesting thing is that by defining this, we arrive to these equations. They are really important. So here we define the output field after the interaction as a combination of the input optical field that was said to be in the vacuum, but in the generality, and the mechanical input field, we say is a thermal field. So this is the full point. In the pulsar scenario, we can write to these relations. These relations basically say that the output field evolves as a two-mode squeezing transformation on the input field. This is two-mode squeezing transformation, and we can write the evolution like that. So we shine our laser for a time tau. When the laser has come out from the cavity, in the Heisenberg picture, this is how the system has evolved. We can do the same trick for the state, instead for the Schrodinger picture, or the Heisenberg picture, and that's it. So now we can start from an initial state where the cavity is in vacuum, we just spoke very quickly, so it's just in vacuum. We have cooled our mechanical stator very close to the ground state. We have now the initial state, the input state. We can evolve using this two-mode physical transformation, and this is just happening to be computed by hand, but you can compute it by hand. You get a final step. We'll see in a second. I think it's quite interesting to say it is exactly the vacuum, so ideally, but the output state joins the overall output state is a state that has EPR correlation between the photons. So it's a superposition of paired photon number states. Now, let's talk about the measurements. We have now talked about evolution, we talked about dynamics, we've seen how the system evolves in time, pulse. Now, we want to take this pulse put a detector and see if we can detect these pulls, and if we detect it, what happens. So, I mentioned before that the dynamics now were quadratic. So, quadratic dynamics preserve the Gaussianity of the state. Vacuum state, thermal state, all Gaussian state. So, if I take the initial state as Gaussian, I put in a quadratic dynamic, this will still be Gaussian after evolution. So, to see negative Wigner function, this does not do the job. We need to introduce another element that is able to de-Gaussianify my Wigner function. And this element is the measurement. Now, homodyne, heterodyne, also quadratic, so they preserve the Gaussianity. Something that is really not quadratic is a post-counting. We project it into Fock state, and we saw at the beginning that Fock state has very non-Gaussian Wigner function. So we hope this job. That's not that. We'll show that this does the job. Pretty nice, I'd say. So here, with generality, D is the dark count rate, so the possibility that the detector to click, even if nothing happens, with no light restriction detector, it can happen, but it stays. And then eta is the efficiency, so the possibility of the detector not to click when lights reach the detector. So lower efficiency means even if I shut that good down, this detector won't click. With this, we can describe the conditional mechanical state upon detection. So I detect laser, what is the mechanical state? We can define we can define this. And the probability of a click to happen, so of my detector to click, they can be expressed like this. And this is a computable object. We can do the calculation and see what they look like. And indeed, they look like something, I think, very nice. So this is the probability of detection. This is the conditional mechanical state with ugly coefficients, but it's just ugly. It would be just ugly. The interesting thing here, the surprising result is that, of course, like the probability of detection gets higher. This term is smaller, close to 1, the higher the efficiency. So, of course, higher efficiency, I expect higher detection probability. But since now the state is standard, the detection probability also depends on the initial temperature of the mechanical state. So, the hotter the mechanical state of the initial, when you shine the fluids, the more likely I will detect something in the optical field. And also, it depends on the squeezing rate. The higher the squeezing, the more likely it is to see an output. Okay, we'll come back to this later. We just comment on the order, and just to kind of say this, we can see the other coefficients depending on initial temperature, squeezing, efficiency, that is a statistical measure of Fock state. So this is easily computable because we know the Wigner function of the Fock state. So W of the state, the Wigner function of the state, will be a weighted sum of these coefficients of the Wigner function of the Fock state. We can compute this and put it inside a software to see what's happened, and that's what's happened. That is what I think is kind of a bit of mine. So, on the x-axis here, the squeezing degree. So, how intense is my laser? How many Fock states I'm able to access with the squeezing I generate. So, the squeezing is generating excitation in the system. The more I squeeze, the more Fock state I excite. On the y-axis, the initial temperature of my system. But in left column, so very small squeezing, everything looks very, very closely to a single Fock state. Because what I'm basically doing for small squeezing is basically the principal process that's going to happen is just a pair generation. So I'm going to generate a photon in the cavity and a photon in the canvas laser. The photon in the cavity will leave the cavity and I will detect this photon. So I'm doing single photon detection. And if you remember, the state was a paired kappa-kappa tensor product of Fock states. So if I measure a single Fock state, the mechanical state will be something very, very close to a single Fock state. So I'm going to say that just to very basically why this is a single Fock state. The more I squeeze, or the higher the temperature, the more top states I'm considering the expansion. So the more fringes I will see around the single Fock state. These fringes are typical of the Wigner state, Wigner function Fock state. So the more fringes I see, the more it's telling me there are contributions from higher Fock states. Now, to be a bit more precise, these are the plots. Left column for fixed efficiency, different initial temperature. Right column, fixed initial temperature, different efficiency. Dark count rates can always be considered to be basically zero in current photodetectors. For example, very common one, avalanche photodiodes, very low efficiency, like between 40 and 60%, but basically zero count rate in the time in the time where the pulse reaches the detector. Only with longer pulse, I will have a chance to do dark counts with the time scales again, no dark counts. Take home message from these plots. I achieved significant negativity, as you see from the other plots, but these negativities don't go hand in hand with probability of detection. So I can achieve very high negativity in the function, but with very low probability of this detection coupling. So I will need to do my experiment many times, and many times, just a small fractions of the run will have success. I will be able to generate condition states of detection. High detection probability means also lower negativity. So something in the middle here, not small squeezing, but like intermediate squeezing around 1 will guarantee a bit of negativity, but also not completely the detection probability. So some probability for the process to happen. And so this could be already the end of the story. I think I just want to have a couple of comments and then I'm done with this. So, first comment, the squeezing rates do not depend on the pulse duration. The squeezing rates are, if I express all the terms with the capital G, the G star, the all that, if I express the squeezing rate, just really depends on I in. I in is the experimental probability, is what I can achieve. Is the power of my input laser, is the intensity, sorry, the intensity of my input laser. So what I deduce from this is open speculation, this is something I'm still thinking of. What I deduce from this is that I have much freedom to choose how long I want my pulse to be. Because the squeezing rate will only depend on the intensity. So let's say now the duration of the pulse matters when we talk about neglecting thermal coherence. So here, this is a condition for neglecting thermal coherence. So if I take smaller tau, it means I can take higher T, higher temperatures. So here in this table, I've got the duration of the pulse in oscillation of the unit of oscillation of the mechanical component, and the temperature for achieving tau 10 times, like this property 10, so 10 times higher than 1. For tau to be 10 oscillation, I need to cool my overall system to 5 to the minus 2 Kelvin. But if I take, for example, the duration of the pulse to be just a tenth of a mechanical oscillation, I can heat up, I can have my system to be at a temperature of 5 Kelvin, which is not prohibitively cold. I think temperatures of 1.05 can be achieved in lab. Still, it put the requirements on the experimental setup. So I thought this is interesting because it kind of relaxes a little bit the experimental assumption to perform this one. Last observation is that we saw before, negativity and probability of detection goes pretty much inversely proportional. It's not exactly inversely proportionality, but very high negativity, very small probability of detection. Now, I mentioned before, I think it's useful to show it, that the probability of detection, let's assume that I will take very small squeezing, okay? Very small squeezing rate, because I have high negativity. How can I have still significant probability of detection if I take it seriously quite big? If I take zero to be quite big, I can take R to be very small. And yes, I will just be detecting a single photon if the detection happens. But the price I have to pay is that my initial state will be very hot. So I will have to consider a lot of Fock state in my initial state. What I see here, I plotted exactly what I say. Well, in the school, let's try what happened if I put the numbers in. Small squeezing, super high initial temperature, 50 photons is quite fast. And what I see is that, of course, I have a lot of ranges, there is a lot of oxides, but I have also like not negligible negativity. Negativity, like here you can see like 0.4. Since quite small, yeah, of course, I like them. They're not too small, okay? No, they're significant. I mean, negativities of 0.04 in this kind of infinite function are not negligible. You're still dealing with a state that has no classical envelope that is somehow still quantum, that has coherences. Finally, just next up, what I like to do next, I like to include thermal decoherence, not just say, well, what if we neglected and just not put the term. I want to consider it. To consider it, we need to go back to the non-German equation and show you the full algebra equation, because that's where you have the capital gamma term, and solve them. One basically have to solve them. You can solve them via the mathematical approximation. One can do pretty much the same thing to find the various matrix. By the various matrix, one can describe the state of the electromechanical system in terms of the Quartz matrix. That is through this. This is the characteristic function, and this means in terms of the Quartz matrix of the refined isolated measurement equation. Capital M is the measuring conditions. This one is a dive because this is the characteristic function of Fock states, and the Wigner function will be a Fourier transform of a convolution integral between the bimodal optical mechanical function and the Fock state for different operation number. That I've done the calculation for a single Fock state, for example, do it for the M case, the case of M photons, the L are the Laguerre polynomials, is not nice. It's absolutely not nice. So even something very heavily numerical, or they can do a different approach here, but still something that is I'm thinking about. So yeah, thank you. Question?
I have a couple of questions. So the first one is about the adiabatic approximation that you made. So this basically is driven by the cavity loss, right? The larger the cavity loss, the better the approximation is. But is this just a technical necessity to solve the problem, or you can sort of relax this condition and, or no, you maybe by doing some numerical study and get away with this large K?
Well, there is you can relax this. For example, if I
mean, do you have some positive effect out of less?
Yes and no. Yes and no. Yes. Depends on what you want to do. If the thing is that you can do the adiabatic approximation when you have this. Right. So let's say I don't know this. Let's say K is similar to G. Yeah. If K is similar to G, it means that you have enough photons inside the cavity to amplify the electron property. And the cavity do not lose photon very quickly. So you have a significant intracavity field. You cannot just say, well, that evolves by itself. By means of this, you will have to consider the cavity field binding as an entity by itself and calculate the correlation between cavity field and mechanical component, and then calculate the output field as a different object. The easy thing here is that we basically cutting out the cavity field. If you want to use the case similar to G, well, yeah, it makes things slightly more difficult because you have to have an extra step in the middle. You have to also first calculate the correlation between mechanical and cavity field, and then by means of this, you want to do another transformation to calculate the correlation between the output field and the mechanical field. One can do it is fully mechanical.
And do you reckon it's going to be some advantage in terms of having some possible states after that? Because having, I don't know, more photons, maybe you have excite more, I don't know, more fringes in your. I mean, you lose less photons, so it's likely that your effectively is having a larger squeezing.
Yeah, I'm thinking because I thought of that. So I think the main problem I face when I try to do this is that these parameters are not really dependent from each other. So achieving k similar to g while still being far less than omega, not easy because you can achieve k similar to g if everything is similar to omega. This is a regime you can actually access, but then you lose the selectiveness of the coupling. You have to consider the both coupling. And this is another part of the work I've put here that is, I don't know if you promise that, very promising. I could do that, but one can achieve in the regime where these three are similar, you can achieve steady state. They are even entanglement, quite good entanglement. An idea I would try is to select an output mode. What I was saying, so we consider these two, which that reach a steady state. You have to use the Gaussian formalism, so you have a bar expansion in steady state. You look to an output node, and from this output node, you try to do everything I've just done. The thing I've seen is that if I ideally perform photo detection inside the cavity, so neglecting the losses of getting out of the cavity, when these three are similar, I get no negativity. Because my interpretation of this is that if these three are similar, you have beam splitter, two mode squeezing, and if they're in steady state, it's because these two are compensating each other a little bit. So one is cooling, the other one is heating. But the thing is that you're heating a bit. In the regime I've looked, I never saw a regime that was cold enough, where the mechanical state was cold enough, where detection, single photo detection, so the hardest photo counting you can do was generating something with negativity. No motion, of course, but with negativity, not very much.
Okay.
It's something still want to explore this. I found a paper that says that it gave me hope basically that says that when you do the output field from the output, so you do these two calculate steady state, when you look just to an output mode, not to the full cavity field, but just to an output mode, what you're doing if you look to a mode around specific frequency, you're doing entanglement dissipation. So there's a chance where the output field is more entangled with the handless later than the output field. There's an eventuality I want to try. Preliminary results, not very encouraging, but I've not really lost hope in this.
I have a question from an online audience. I think Sylvia wanted to ask.
Yes. Hi, can you hear me?
Can you raise your volume?
It's oh, that's why it's in the earphones. Sorry.
Hi, can you hear me? Can you hear me?
Yeah.
Okay. Can you show again the Can you show again the Hamiltonian after linearizing and in this interaction picture? Yeah. So I would like to understand why when you are in the blue detuned regime you get entanglement. I didn't get that.
Okay, good point. So Mauro educated me with telling me first in the beam splitter regime, if you put two thermal states with different temperatures through a beam splitter, so in the case where I'm considering vacuum and thermal state, through a beam splitter, you will get discord, but not entanglement. So the first one generates no entanglement. The second one, going towards the blue detuned regime where you were asking me, I think it's clear if we consider, let's apply this Hamiltonian, let's evolve with this Hamiltonian with the two mode squeezing coupling, a vacuum state. If you do this, what you get is this psi out. It's a calculation you can try to do. You can try to do by yourself. You take Hamiltonian, which is two mode squeezing. You apply this two mode squeezing at a vacuum state, a two mode vacuum state, and you see the final state. Now this state is not only entangled, it has EPR correlation, which is a stronger form of entanglement. If you know better than me, I'm not really an expert at this, but I know it's a stronger form of entanglement. So I think an explanation, like intuitive explanation I can find is that here, if you measure one, the other one will feel a strong effect. That is pretty much the base of entanglement. I think it's pretty intuitive. Like, it's not formal, but I hope it's intuitive enough.
Okay, thanks.
Welcome.
So the other question is that I want to ask is it's just a comment. I don't know what it is. So you consider at the beginning a coherent state to push to drive your system for the beginning, right? And then you do lots of a couple of approximations and so forth. And you thought, what do you think would happen if you start with a Gaussian state, but a squeezed state to start with? Because do you think it's going to cancel your non-linear effect, or maybe with a squeezing?
I think what canceled the effect was not really the initial state. Maybe this the disambiguation. It was coherent drive.
Yeah, coherent drive.
Yes. So you asked me, what if you drive your system with a
squeeze line to start with, instead of a coherent state? So, I mean,
are you thinking
it's already a non-classical state of line, but Gaussian in a way. Maybe you don't get it for free because you have to invest in that. But maybe in some conditions, the squeeze line amplify the coupling rather than I don't know.
Let me just ask you to clarify. Are you thinking about having light with squeeze correlation, or putting a parameter amplifier inside the cavity?
Exactly. Parameter amplifier inside the cavity.
Hello, that was talking with you. Good idea. I have no idea, and that's something that the only problem with that it's stability. But I was looking into this a year, 2 years ago, and there were stability problem on the steady state with a pulse. Maybe a great idea.
Also with the linear maybe through the study, the K-term is really study problem that kind of cure.
Could be. I think when I watched that, it was like if you drive a bit too strong, everything explodes really, really badly. So I gave up on that route, but I never looked through the pulse, because with the pulse you can just neglect stability conditions. Like in the Bluetooth regime, you won't get any steady state. You need a mixture of cooling and heating to get a steady state. If you just drive on the Bluetooth on this Bluetooth sideband, everything explodes. Right? You're heating your system and everything. You break your system. No, that's a really good question. That's something I was wishing to look into. Really interesting. Thank you.
Any other question? Not last time on the right.
Che carino come